Okay, so now I need to understand how this function will change as a function of x, right? I have this regression function. It's the conditional distribution of y, expectation of y given x, okay? When I'm looking at this plot here, I don't really need to tell you much, okay? I could actually literally break my data set into 4 parts and work on them separately. There's enough data that I don't actually need to borrow information from different age groups to understand what's going on, right? I could just say, okay, here's the conditional median for that group. Here's the conditional median for that group. Here's the conditional median for that group and for that group. Now, if you go back to the continuous example here, what is the conditional expectation for 500, for example? Well, I don't have any data point here, so it's not like I can actually isolate all the campaigns that invested, $500 and look at the conditional expectation or the conditional median of that guy. I just don't have data. So somehow I'm going to have to pull information from my neighbors. I'm going to have to pull information when I'm trying to predict what's happening at, say, $300. I'm going to have to pull information for things that are close, or even hopefully from all of the points. And the way you do this is by imposing some structure on what this function can be. Okay, so here, this thing was drawn by pulling only information locally. Everything that's close is actually giving me some information. But when you do linear regression, you're actually getting information from all the points to estimate the conditional expectation at one point. Okay, so this is how we do this. So first of all, we focus on, so now we're talking about regression. So forget about conditional median, conditional quantiles. We're never going to talk about this ever again. But I just want you, my main goal here is to convince you that regression is not the end of the story. There's many conditional aspects of this conditional distribution of y given x that you could try to understand. Okay, so, sorry. Where am I? Okay, so first of all, we're going to focus on the modeling the regression function. Anybody remembers the definition of the regression function? Let's learn it now so we don't have to do it later. Of y given x is equal to little x, okay? So that's the regression function again. Now, this is a function, and we saw at the very beginning that if I wanted to give you, the reason why we talk about parametric families of distribution is because we want to summarize something that could be described by a full density with something that's actually much, much simpler. That's described maybe by one real parameter or maybe 2 real parameters. And we're going to do the same thing here. So here, the function f is not a density, right? It's not a non-negative, not necessarily a non-negative function that integrates to 1, but it's still a complex function. There's even more of those guys because I don't have those 2 constraints. And so I have a lot of functions. There's an infinite number of them. And so I cannot really just try to estimate it if I don't tell you what this function looks like. Okay? So it could be really anything, especially in between the points that I don't see. Right? When I see a point, I could say, well, this is the value of my function. And when I don't see it, I could put 0 or 27 or 2 pi over 6. I could put whatever I want. And so if you allow any function, it could be completely crazy. So what we're going to do is we're going to allow for a limited number of functions. We're going to restrict functions that are plausible. So the first thing you might want to do is to say this function is smooth. It's not just jumping from one point to 2 pi over 2 whenever it wants. And that's what you actually saw in the first case, and this is the purpose of non-parametric estimation. We're not going to go there. We're actually going to go back to the parametric example that we had before, and we're going to try to parameterize this function using 1 or 2 parameters. Okay? Just 1 or 2 values. And so the simplest functions I can actually think of are functions of the form a plus bx. Actually, the simplest functions I can think of are the functions f of x is equal to a. All right? Actually, f of x is equal to 0, and then I can just go home. But if f of x was equal to a, what I would effectively be doing is saying y does not depend on x, or at least the conditional expectation of y does not depend on x. It's just a constant value no matter what x is, which would amount to having this blue line being horizontal. Right? I want to say that maybe, the more I invest, the more I'm actually getting back. So I want maybe this function to actually be increasing. And so I'm going to allow to have a little slope here. So those functions are called typically linear. Actually, affine is the real word because I allow for an intercept. But since we talk about linear regression and not affine regression, this is the preferred terminology. Okay? So we'll think of those functions as being linear, and those are essentially the simplest possible functions you can come up with that will display a dependence of y on x. Okay? And so under this assumption, we talk about linear regression. Okay, so that's what linear regression is. It says so I don't make any assumptions by assuming that x and y have a joint distribution. I don't even make any assumption by saying I'm only interested in the conditional expectation of y given x, right? The regression function. That's just myself limiting myself to what I actually want to learn about this distribution. But at the end of the day, here I'm making this very actually strong assumption that says that my function, my conditional expectation is actually a linear function. So pictorially, this is what it looks like. If this is the truth, for example, what we're assuming is that, well, the truth is not that complicated. Maybe the truth is slightly simpler, and I really just have a straight line. And it's not that far. And in many instances, it's not that far. Now, there's other instances where it will be that far. All right, so for example, I can think of an example where there's this is a so-called motorcycle data set. So I think it just takes a motorcycle, hopefully with a crash test dummy, put it in the motorcycle and just send it on a wall. And you can see that they have an accelerometer on the helmet, and it just goes up, and then of course it goes like this. And so if you look at what the regression function should look like, is like, okay, I'm accelerating, then I'm not accelerating, and then I just have this little oscillation like this. Okay, and so all my points look like this. So there's less points here, and then here it goes like this. I'm not going to put a straight line through those guys. I need to actually be smarter, and that's when you actually need to resort to non-parametric statistics. But for the purpose of those simple things, we're actually here. You could actually probably guess from physics what the shape of this guy is. Make a transformation of your x so that you actually only need to guess maybe the tilt or something like this with this curve. So you can do data transformation before you do linear regression, right? You could not do y onto x, but y onto some cosine of x, for example, or x squared. Okay.